Alright, so recurring theme was help on number 60, so instead of going around all the individual tables and helping on that, let's do that together. So this one says use a method of your choice to find all horizontal and vertical asymptotes of the function 4 over x squared plus 1. Okay, so we're going to use all the methods available to us. The first one is algebraic. Okay, and so which one do you want to do first, horizontal or vertical? Vertical. Okay, vertical asymptotes occur where? Yeah. Mumble, mumble, I'm kind of hearing it.
I don't have to do it. I know
The what?
the y.
The denominator is equal to 0.
Okay, cool.
Okay, so here's the funny thing about this one. X squared plus 1 equals 0 when? Nunca, never. Yeah, doesn't ever happen. Okay, so that means that we're led to believe that there are no vertical asymptotes. Okay?
Why is that?
Yes. Why will this never equal 0?
Yeah.
Because if I try to solve this for x, my instinct would be to subtract 1 from both sides, and then take the square root. And unfortunately, the square root of -1 doesn't exist.
Well, that's why I wrote the equation.
It's an imaginary number. Okay. All right. How do I find horizontal asymptotes?
It's the exponents on the
Right, highest exponent on the top divided by the highest exponent on the bottom. And so for this one, then we only have to look at 4 over x squared. And then just think about when x gets bigger and bigger and bigger and bigger in either the positive or the negative direction, what happens to the value of this fraction? In other words, what I'm asking you is, what is the limit? Yeah, as x approaches, we'll just do them both at the same time, positive or negative infinity of 4 over x squared. 0. The bottom gets very large, the top just stays at 4, okay? So that's going to approach 0. So that means that I have my horizontal asymptote. Such a long word to write. Is y equals 0, okay? So those are our suspicions from doing a little bit of algebra. Let's take a look at the actual graph and see what we have won.
In this college.
Yes.
Where's the mouse at?
Where's the what?
The mouse.
Oh, it's over here. You want it?
Yeah. Oh, also, good.
Okay. All right, so we want to see what the graph of 4 divided by x squared plus 1 looks like. So there it is. Okay. So this confirms the algebra that we did. You can see that as x gets bigger and bigger and bigger and bigger, the graph gets closer and closer to 0. Same things happens on this side when x gets smaller and smaller and smaller. So I have a horizontal asymptote of y equals 0, and I have no vertical asymptotes. All right? Good? All right. Other big ones while I've got you.
No, you're right. We don't.
Okay, so keep. So today, super exciting day because we get to talk about. Thank you. The 12 basic functions. Okay. So what we're going to do is we're going to go over 12 functions, their equations, their graphs, and a bonus interesting fact about each one. Okay. And then. Tomorrow, when you come into class, the first thing that we will do is I'll hand you a blank piece of paper, not blank, but it'll have the functions on there, and then you, without the help of a calculator or anything, just from, because they're just basic, will sketch the graphs of these 12 basic functions. Because these are ones that you just have to have. They're just like, oh yeah, all right? Okay, you ready? Okay, yeah, you're ready. And then we'll spend the year basically like just talking about adjusting these and blah, 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 blah. Okay, so here is the first of the 12 basic functions, okay? You can get this one. This is our old friend, y equals x, okay? The most basic of all functions in the world, okay? Straight line, all lines are straight, goes through the origin, slope of 1, okay? Now, some of these interesting facts are interesting. Some of them not so much, because they have to come up with one for each one. This is not really a very interesting fact, but this is the only function that acts on every real number by leaving it alone. In other words, if you picture the pre-algebra or first-year algebra function machine, and a function is you take a number and put it in there and then it spits something out, this function machine does nothing, okay? You put in a 3, it gives you a 3, you put in a -4, it gives you a -4. Isn't that interesting?
Yes.
Yeah. Okay, so everybody knows that one, good old y equals x, okay? Then we have our old friend, a parabola, okay? Y equals x squared. So everybody in here should already know, if I just said, earlier today, what does the graph of y equals x squared look like?
Quadratic.
Oh, yeah, it's a parabola, it's a quadratic, okay? A little bit more interesting, the graph of this function called the parabola has a reflection property that's useful in making flashlights and satellite dishes. And what that's all about is that if you picture this like in 3 dimensions, like you take this parabola and rotate it, okay? There's a place, and we're going to talk about this later in this class, inside this parabola that's called the focus. And what's cool about the focus is if you take like a light source and put it here, and all of these things shine at the flashlight, or at the parabola, I mean, they will all be reflected parallel to each other out of the flashlight. Okay, so your headlights, your car, flashlights, those dishes are all parabolic. They're called paraboloids. And it's nice because you get this nice focused beam. It doesn't disperse, so it's bright. The opposite then is true for satellite dishes. If you have a satellite dish, they put the little signal receiver right here, and then all of the signals come in from outer space, and they all hit this parabolic dish and then bounce right into that little focus point, and then, I don't know, little tiny men run around and turn that into a TV picture somehow in your house. I don't know how that part works, okay? But that's why dish is a little bit of an issue, because if you have a storm and this thing blows around a little bit, then this jiggles and then you lose the focus, okay? So I don't know if anybody has Dish Network, but they've got to mount it. Does that happen sometimes where you lose that? Yeah, okay, that's why, because the focus is moving a little bit, okay? All right, what's the next one going to be? Yep, y equals x cubed, the cubing function. And everybody knows what that looks like already, probably, maybe, before you came in, okay? The interesting fact for this one is that the origin, and this is what Evan was asking about when we came in, has a special name. That's called a point of inflection, okay? And so some of you asked, what's the deal if it's not a local maximum or a local minimum? That's what this point is called right here. And you can kind of see that it's changing from, this would be called concave down, and this is called concave up, okay? Well, right in between those two things is a point of inflection. And we will study those in great detail together next year in calculus, okay? Okay, I do not believe that we go to x to the fourth, because that's not very common, so I wonder what's next. The old reciprocal function, okay? So this one is 1 over x. So it has two simple asymptotes. It has a horizontal asymptote right here, and it has a vertical asymptote right there, okay? And you can kind of get the shape of the graph just by understanding math. If I plug in very large numbers of x, then it's going to get closer and closer to 0. If I plug in numbers that are in between 0 and 1, then like 1 divided by 0.5 is actually 2, right? And 1 divided by 0.25 is 4. And so as these get closer to 0 but stay positive, this is going to approach infinity. And then the opposite happens when you deal with negative numbers, okay? So the interesting fact here is that this curve, it's called a hyperbola, also has a reflection property. The thing that I like about this one is that if you take this and make this three-dimensional, and then you tilt your head sideways, what are we looking at?
Nuke tower.
The nuke tower, yeah. So the nuke towers that you drive past all the time are based on this curve. The engineering that they use to build it is based on, it's obviously not just one over X, it's a little more complicated than that, but it's the same sort of idea. Okay. What's that?
3 total, so that's a little bit more complicated.
Yeah. While we're talking about the nuke towers, the interesting fact about those, I heard, don't know if this is true, that when they made those, it was one continuous pour. So they were pouring and then building the forms as they went, and they just never stopped pouring the concrete until it was all done, because they wanted it to dry all together in one big piece. So
It was a waste.
it was a waste, and my father lost money on that. He invested in it, and they went bankrupt, and he lost, but they should have known that, because the acronym for it was like WHOOPS. That's what, I mean, it was the Washington Harbor something power or something, and it came out to be WHOOPS. Yeah, and then again they went, whoops, okay. Nuclear power didn't take off like we thought it did, oh well. Okay, so that's the reciprocal function, okay? Then you've got the old square root function. Square root, yeah. And you can again just sort of figure this out by doing math. The square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2. So as these numbers get bigger and bigger and bigger, the y values do increase, but at a slower and slower rate, okay? Interesting fact about this, put any positive number into your calculator, take the square root, then square root, then square root, and eventually you always end up getting to 1. So give me a number. 5, okay, we can start with 5. I'll do it on this one because I don't know that it'll work on Desmos, but if I start with 5 and take the square root and then just keep hitting nope, then I need to take the square root of the answer, and that's not the square root. Then I need to take the square root of the answer, and then I think now it'll keep doing the, square rooting. And so if I keep hitting enter, and keep hitting enter, and keep hitting enter, and keep hitting enter, eventually it's going to end up equaling any day now. Eventually, it's just one of these, okay. We'll be done with pictures before we're done with the square roots of all of these. Eventually, almost there, 3. Oh, man. You're not going to let me stop, are you?
You're there we are.
There we go. Eventually you'll get to 1, okay? If you keep doing that. When this book was written, maybe the calculators weren't quite as fancy as they are now, and so it didn't take quite as long, but there you go. All right, next one. Okay, so now things get a little bit tricky. Some functions that maybe you're not 100% familiar with. So this is y equals e to the x, okay? E is comes from the natural log. Remember the natural log? We're going to talk about that one in the middle in a minute. Those two are inverses of each other. And so the interesting fact is the number e is an irrational number like pi that shows up in a variety of applications. What's one application that we talked about e with? Anybody remember?
Shipping, right? Didn't we talk about that? Remember you're like, remember like the chart thing, and you're like,
banking, right?
shippers from a long time ago, they're like, hey, we'll use
Oh yeah, when the juniors were at Business Week, right? That's right. Yeah, that's absolutely right.
Look at that.
Hey, nice one, Joseph. Yeah, totally forgot. So when they were doing like their accounting, they used exponential functions to make it easier. Good. Yeah, awesome. And then also, in banking, if you have interest that is compounded continuously, then you use E as your base, okay? Both of these symbols contributed to the great Swiss mathematician Leonard. When I first went to school, this was pronounced Euler, and then somebody decided that they should pronounce it Euler. So I don't know what it is, but if you go to college and to take a math class, they might talk to you about Leonard Euler. Okay? All right, inverse of that is the natural log function. So if you remember inverses, if I could superimpose that last graph onto this one, they are reflections of each other across the line y equals x. So they're inverses of each other. This is my favorite interesting fact of all. This is why I get excited about this day, because of this one right here. It just blows me away. It says this function increases very slowly. Okay? If the x-axis and y-axis were both scaled with unit lengths of 1 inch, so we made these spaces be 1 inch, you would have to travel more than 2.5 miles that way for the curve to get 1 foot above the y-axis. Okay? So it is increasing, but super, 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 super slowly. Okay? In other words, if you take the natural log of whatever 2.5 miles is in inches, you get 12 as an answer. So that's pretty crazy. Okay? All right, then back to our study of trigonometry, we have our old friend, the sine function. So you remember from last year that sine goes with the y coordinates as you go around the unit circle. So if you start right here and move your way around, this y coordinate is 0. Then we're talking about the unit circle, so the highest it ever gets above the x-axis is 1. So that's why the sine function tops out at 1, and then it continues back down here to where it equals 0 again, and then it goes into the negatives. The lowest it ever gets to is -1, and then it gets back to 0 again, and then repeats the whole process as many times as you would like. Okay? So the key points there are that the sine function starts at 0 and then increases. Okay? How long does it take for it to complete one cycle?
7.
Nope.
6.
Nope.
5.
Nope.
3, 2, 1.
I wish something exciting happened then. Nope. 2 pi. Okay? Because the circumference of this circle is 2 pi if the radius is 1. So the period of that function is 2 pi. Okay? Interesting facts, this function and the sinus cavities in your head derive their names from a common root, the Latin word for bay. This is due to a 12th century mistake by Robert of Chester, who translated the word incorrectly from an Arabic manuscript. Okay? So bay, like your sinuses, that's the correct translation because it's in the shape of kind of a bay. And then this was some other thing, and he wrote it down wrong, and now we're stuck with sine because of this loser right here. Okay? So Leonard Euler, great mathematician. Robert of Chester, not so much. Okay, next one is cosine. Cosine is associated with the x values on the unit circle. So the x coordinate right here is 1, so that means that the cosine function starts at 1. And then when it moves around the circle, what happens to the x coordinates? They decrease. So you start at 1 and then you go down. Right here, the x coordinate of that is 0. And then if I keep going, then this will give me an x coordinate of -1. And then just like with the sine function, I go all the way around and then start again. Okay? The interesting fact about the cosine function is that the local extrema of the cosine function occur at the zeros of the sine function and vice versa. So they're sort of just translations of each other. Okay? Right, we doing okay?
Yeah, we're about tangent.
Okay. Tangent has a very strange graph that is not very useful, so we don't consider that a basic function. We don't spend very much time with that graph. These graphs have tons of uses, so we talk a lot about sine and cosine graphs, but tangent not so much. Okay, next one is the absolute value functions, has a V-shaped graph. You studied that all the way back in algebra. That was one of the families of functions that we looked at. The interesting fact about this is that this function has an abrupt change of direction, which we call a corner at the origin, while all of our other functions are all smooth over their domain. So this is a function that math teachers like to throw at you a lot because weird things happen to the graphs. So for example, what they're saying here is that this is a continuous function. There's no break in the graph, but it's not a particularly smooth function, okay? It has that abrupt change into it. Okay, when I first taught this class out of an earlier edition, it was only 10 basic functions. Then they threw in these 2 extra ones. These are not very basic functions, so these might be extra credit ones on the quiz, on the whatever quiz you want to call that tomorrow. This is called the greatest integer function, and the way that this function works is you take a number, give me a decimal number, 0.1. And the way the greatest integer function goes is if you, 0.1, you go to the number that's just below it. You basically just truncate. You don't round, you just make it disappear. Okay? So 0.1 becomes 0. 0.5 also becomes 0. 0.9 also becomes 0. So all of the numbers in between 0 and 1 get rounded down to 0. Okay? So then if I go like 5.7, that gets rounded down to 5. Okay? Yeah, and it is on your calculator. You can graph it using this int thing. But again, it's not a very useful function, but it's fun to talk about in math because of all of the discontinuities that show up. But I don't consider this to be very basic. Okay? Okay, and then the last one is a logistic function, which again, if you look at the equation for this, is not very basic at all. We will study this in greater detail in this class. I didn't learn about logistic functions until, how old are my children? Maybe 15 years ago, I went to a conference, a math conference up in Forks, Washington, and we were talking about tree growth, because there's actually a UW satellite thing there. Yeah. It was 2 weeks, though, in Forks, Washington, and I went with Mr. Helby.
Oh, man.
I don't know if I can.
It was a struggle. It was a struggle. The interesting thing about these is that logistic functions actually do model a lot of real-world growth. So when you think about the growth of a tree in a forest, it starts out to grow very, very quickly. It starts out exponentially, okay? And then, as the other trees in the forest start to grow as well, and they compete for resources with each other, that rate of growth slows down until it reaches a maximum value, and that's called the carrying capacity of whatever that is. And so what do we do as managers of forests, as loggers, to make this growth occur again?
Replant.
You don't necessarily replant, that's when we cut it down to 0, okay? But once you get to this stage, anybody have family in the forestry industry? You go through and you thin out the smaller trees, okay? And then that allows these trees to enter another period of logistic growth, okay? So you get rid of the small ones, give more room to the ones that are strong and doing well, and then they will grow bigger again. That is the problem with much of what we do in this country, is we don't thin anybody out, okay? Everybody gets a medal, everybody's a winner.
Everybody gets participation awards.
Right, everybody gets a participation award, and so everybody thinks they're great, and so you reach a point where you just can't go any higher, okay? Gardeners, you do that also, right? If you ever plant a garden, you go through, you throw a bunch of seeds in there, and then you go through and you pull out all the little tiny sprouts and keep the big ones. Same deal. All right, so let's have some brief mathematical conversations about some interesting features of these. 9 of the functions have domain the set of all real numbers. Which three do not? Which three of these functions have holes in their domain? Or missing pieces?
Integer greater thing.
No, actually that, you can plug in any number. That has, it's,
No, but it has holes, like.
Yeah.
right, but the holes like match up.
Square root function.
Yes, the square root function is not defined over all the real numbers because you can't take square roots of negative numbers. What else?
Reciprocal.
The reciprocal function is missing what?
Natural. Certainly.
0. Okay, yeah, you can't go 1 over 0. And then Joseph, you said?
What?
You said what?
None.
Yeah, you did.
Did I?
Yeah. You said natural log. Okay, the natural log function, you can't take the natural log of a negative number. So those three don't have the domain of all real numbers, okay? One of the functions has domain the set of all reals except for 0. Which function is it? We just talked about it? The reciprocal one. 1 over x, you can't plug in 0, okay? Which two functions have no negative numbers in their domains? Square root and
Square root.
natural log. Which one of them is defined at 0?
And any positive natural.
So natural log is not defined at 0, the square root is. You can take the square root of 0. You can't take the natural log of 0 because remember this would be saying that my base is e. So if I asked you the natural log of 0, I'd be saying e to the what number equals 0. And you can never take a positive number and raise it to a power and get 0 as an answer. You can get as small of an answer as you want, but you can never get 0 as an answer, okay? All right, only 2 of the 12 functions have points of discontinuity. Which ones have points of discontinuity?
The integer.
The greatest integer one, and which else?
The smallest integer.
Right. What else has a point of discontinuity, a break in the graph? The reciprocal function, okay? Are these points in the domain of the function? So Nate said that last time. So in the greatest integer function, those points are in its domain, but in the reciprocal function, 0 is not in that domain, okay? All right, only 3 of the 12 basic functions are bounded both above and below. Which ones? Cosine and sine are bounded above and below. And what's the last one?
X squared.
X squared goes up forever. Square root can go up forever if you keep putting in bigger numbers.
There's an algebra.
What was their question?
The logistic function, yes, that one has, those 2 lines are the boundaries of that line, okay? So it's bounded above and below by that line right there, okay? Good. Okay, 3 of the 12 basic functions are even. And when you're talking about graphs, the way to find out whether it's even or odd is just to look at symmetry. So when they say even, they're saying they're symmetric with respect to the y-axis. So what 3 of these functions are symmetric with respect to the y-axis? X squared,
Absolute value.
cosine, and absolute value, okay? Sine is not because it's shifted off. But that's the next one. No, it's not. Okay, it says we can continue to explore the 12 basic functions, but what we're going to do starting maybe tomorrow is we're going to move them around a little bit, okay? But we'll talk about that later. So for right now, how about more fun questions for you to do on your own? Oh, the cheers like it's raining down. Don't forget. The love sometimes.
Oh, wait, you take some, you guys have to just do 6 hours. What is it? What?
Yes.